themselves, and then if you have a question, unmute so that we can hear it. But we'll turn it over to Bern.
Okay, so everybody
okay,
you should all be seeing this well screen.
Yes.
Okay, so like I say, Sarah says holler, because now I'm sharing the screen, and Sarah can watch the participant list there, and I guess we could probably chat, can't we, Sarah?
Yes.
Okay, so anyway, throw that in. All right, so what I was asked to do, as I understood it, was just to let's talk about wells, and we geologists basically are trying to encourage people to think, you know, the landscape in 3 dimensions, and the well is that 3rd dimension, the z of the XYZ coordinate space. So I thought I'd just walk through for folks what is a well and what do they mean, and particularly in the context of the Casper Aquifer. So if I can get this to page down for me, boink. There is the cross section that we all have come to know and love. Recharge area up in this area of the Casper Aquifer exposed at the surface from the east edge of town to the top of the range. Municipal wells sit right here, just right on the thin edge of the overlying Satanka Formation. And then out on the Casper Aquifer, we have a whole series of private wells. Those are detailed as we blow those 2 up. Municipal wells, they tend to be deeper, penetrating multiple beds within the Casper. So we have a sandstone, limestone, sandstone in this particular picture. The municipal wells are bigger. They have pumps in them capable of extracting up to 1,500 gallons a minute. The municipal well, or the domestic wells are, of course, much smaller and typically shallower because they don't need access to that much water. So they typically will access 1, maybe 2 of the different units within the Casper Aquifer. And once you're outside the city and you're off city sewer, then each of the residences on the aquifer has an associated septic tank and drain field, which then become a source of low-grade kind of drip contamination. And we tend to focus on septic systems. That's really not quite fair. Associated with life in America are lawns and oil changes and antifreeze, and just the footprint of a residence on the aquifer includes many opportunities for low-grade contamination through accident spills, over-application of fertilizers and pesticides, as well as the daily drip of the septic systems themselves. So we talk septic systems and nitrates, but that's a surrogate for just anything from the surface. Okay. All right. So then I did a little video here that I couldn't figure out how to turn it sideways, so you'll have to bear with me. So we're going to drill a little well. All right. So here's Bern out in the garden, and what it takes to make a well is you got to make a hole in the ground, and then you got to get the stuff that you have to loosen everything up, and then you got to figure out a way to get it out of the ground. That's what I'm doing with my post hole digger here. So then the question is, how do you keep the hole from collapsing back on you, like if you're drilling a sand in the beach? And so what we do is we put a piece of casing in the well to hold the dirt out of our well. That, of course, leaves quite a space around the casing, which I'm pointing to there. And then we fill that in, either in this case with dirt, which is a very low rent way to seal things up around the casing, or we could fill this space with concrete or bentonite or something else to seal up our hole. The casing keeps the loose dirt and rock from collapsing in on us, and then the seal keeps stuff from running down from the surface. Okay, so that's one way to dig a well, would be with a post hole digger. Obviously has some limitations in terms of removing dirt from the hole. Is what you find pretty soon you're down to where the handles won't grab anything anymore. All right, so here's another little video where I'm offering a different way to drill a well. Okay, here we're going to jet our well down. Instead of trying to use the post hole digger, I need some way to automatically bring the material up out of the hole. So let's give up on the post hole digger, and we're going to just drill this hole with a garden hose. So I can put that hose down into the dirt, and then it washes the dirt up out of the hole as I go, and I can keep feeding the hose down into the ground, and presumably if things were loose enough, I could make substantial progress with my garden hose. And basically what I've done there is the way modern wells are drilled, and we can introduce that garden hose into the ground, and on and on and on and on. So here we have the way most wells, this would be the post-hole digger approach. Many wells in the world, perhaps most, if you get outside the developed world, are hand dug. And so in this case, here's my post-hole digger. He's standing down at the bottom of the well. Somebody puts down a bucket for him to load the dirt in. And then for casing, they've lined the well with brick. In some cases, the wells don't even need that. But you can dig a hole most anywhere on Earth. If you go deep enough and let it stand long enough, it'll accumulate a little bit of water. It may not be enough to do anything useful with, and it may not be fit to drink. But in most cases, there's water down there somewhere. And as I say, most of the world, when they're drilling a well, they either paw out a hole as an elephant or a horse will do. Humans are a little more ingenuity, have a little more ingenuity, and will actually dig a well. So they end up looking like this. Now, this one they didn't need to case because apparently the earth materials were stout enough to hold up by themselves. And then she's just run her bucket down there on a stick and pulls the water out. But basically, same story everywhere you go. In the developed world, most wells look like this. So there's a borehole that you've created with a tool of some sort, and then inside that is a casing, and this can be typically steel or PVC. In the old days, in some places, bamboo, if you knock the segments out, has been used for casing in ancient China. Most of the wells you'll see in the United States are going to be either PVC or casing. So we have the borehole, the casing within the borehole, and then we've drilled down to where we've hit water, and then we have to have some holes or something in our casing to let the water come into our well. So the missing piece from the diagram would be a pump that we would set about here, and then that would pump the water up out of the casing and off to our house or where we were trying to use it. And that is done with a drill rig. So if you're with me with the shoving the hose in the ground, all right, I can't go very far, but if I wanted to go further, I'd put some teeth on the end of that hose, and then I could kind of grind it around. Then I would substitute for my garden hose a piece of pipe that would have some teeth on the end of it. But I'd still be squirting the water down through, so that as those teeth down at the end of my hose now pipe ground things up, then I was flushing the grindings up the sides of the hole. And what I've described there is a modern rotary drill rig. So the way we drill wells these days is here's what's called the drill stem, is this piece of pipe, and on the end of it is a drill bit that's got teeth of varying sorts on it, and rollers and grinders, and there's a million different kinds of drill bits. And one spins this drill bit on the end of this pipe. So the machine is set up to grab that pipe and spin it around. So it grinds things up. And then the machine is also set up to pump a fluid down the drill stem, out the bit, and up the sides. So I've blown that up here. So down the hose, the drill stem, we will pump either water or a thin mud or even just air. And then that will pick up the cuttings that are created here at the bit face and circulate them back to the surface up the sides. In this diagram, it's very commonly the case, then we circulate the fluid, whatever it is we're using, mud, foam, air, diesel fuel, anything that will pick up the cuttings are used in various situations. And then in this case, he's thrown out into a pit, some kind of a way to let all the dirt and mud settle out. If you're using a non-air fluid, then you pick that back up with a mud pump, and it circulates it back down the hose and picks up more. So basically what you're looking at here is the same thing as me shoving my hose into the garden. And this very same process works for wells 50 feet deep or probably 30,000 feet. And there are 28,000 foot deep wells in Wyoming, and that's the process. This little rig wouldn't do that. What you'd see is probably a 3-story rig with a 100-foot derrick, but the process is exactly the same as shoving a garden hose in the ground. The drill pipes come in 20 and 30-foot lengths, and as you get bigger and beefier, those pipes can be as much as 6 inches in diameter with 1-inch thick steel walls, and they just feed them into the ground one after another. It's hard to imagine drilling 25,000 feet with 20 or 30 foot pieces of pipe, but that's how it's done, and then off you go. So conceptually, very simple. Technically difficult, expensive. Wells can cost anywhere from $1,000 for the shallowest domestic well to $10 million is down the line for a deep oil or gas well. My little drill rig here is drilling a water well. He's going to keep grinding this away until it gets down to the water table, he or she, and then we'll go ahead and put some casing in the hole and have us a well. Okay, so that's what you see when somebody's out there with their drill rig. Turning back to the local situation, so what we want to do is we're going to grind our drill rig down through all these layers. This is a picture from the Wendy's parking lot, where some of you have been. Here's a limestone layer. That's pretty hard, so you're going to have to grind on that a long way. And then you'll get down into some of this softer material, some of these sandstones, some nice shales down here, and you'll probably be able to grind your way through that pretty well. And then all that's coming back to the surface, either with compressed air or with a thin mud or just water. And in the end of that process, you've got samples that you've taken as you drilled along. So here I am at 100 feet, and I grab a little bag of stuff, and I go down to 105 feet and drag a bag of stuff. What you see here laid out on my office floor is a well that we're working on up at Jackson, and each one of these little baggies is full of dirt that came from a different depth. Circulated back to the surface with a thin mud system in this case. And so here's a sample of drill cuttings, as they're called, that came up from a limestone layer. We ground it all up into this size chunks, and then we look at those and try to figure out what they are and what's down there, and then we can note accordingly. And for that well, here's one where we got into a sand that basically didn't break off in chunks, a few little chunks, but mostly it's just loose sand. Here's a place where you'd have trouble with the hole collapsing on you if you didn't put some kind of casing into it. And when we're done, then we develop a well log. This is one, I don't think it blows up all that well, but this is one that Chris Moody did for the Soldier No. 1 well, one of the municipal supply wells here in Laramie. And he's broken out each little layer as he was going along. He found a limestone here, sandstone and sandy shale, thinly bedded white limestone, interbedded pink and red sandstone, and so you'll get varying degrees of detail. But if you've got a competent geologist on the well, they will turn out a fairly detailed log. Satanka shale up here, and then he called it the top of the Casper Formation right here at the first of these sandstone layers. But part of the point of this exercise is that it isn't like the hole declares itself, oh, I'm Casper Formation now. One has to look at these cuttings and sometimes look at them quite carefully and make a determination whether you're still in the Satanka shale or whether you've penetrated down, say, into the Casper Formation. That's an important benchmark in drilling a well in this area. And then what Chris is showing us on the right-hand side is how the well was completed. So here's the casing that was put in, the seal around the casing, and we'll talk a little bit about that in a minute. And then in this case, the lower part of this well is open hole. It was stout enough rock that you could drill a hole in it and it would not collapse back on you. Now, much more commonly, what we see are logs that are submitted with the well on a domestic well, something more like this, because the state requires you to get a permit and to declare what you actually did. So this is a well log from one of the wells out on the aquifer that was done for a domestic well, just by the driller. And some of the drillers are better than others, and you learn the local drillers as you work with a lot of these logs. In this case, the driller felt that he was confident that he was in the Satanka red shale because of its color down to 80 feet. And then at 80 feet, this driller decided he was in the Casper Formation. We have to decide whether we believe him or not. But no, not an unreasonable thing to say. He doesn't tell us much about it in terms of whether it's sandstone or limestone, but he's told us that in his opinion he's in the Casper. So we can look at a bunch of those, make up of what we will. Now let's see, where am I? I'll probably back up. Figure out where I am. Okay. Sometimes these individual logs that you'll see won't attempt to call out the formation, and we geologists actually would prefer that the driller not get too carried away. We'd rather have them tell us what they see and let us decide what it is. So in this case, our driller has told us he's drilled 3 feet of just loose material and then clay. That's probably Satanka based on these location. Sandstone sounds kind of Casperish, and then he's hit a lime rock here, and we might be able to match that up with one of the limestones in the Casper and convince ourselves that he actually hit the Casper formation at 18 feet. But one has to work with these, and the point of sharing this with you is these are the raw data that we have to map where the 75 feet is, for example, and why there are legitimate disagreements among geologists of exactly how thick various units are, because we are often trying to interpret data that is less than precise. Fortunately, we have the municipal wells that are typically, well, not typically, they're always and often required to be monitored by a professional geologist who is sensitive to the kinds of things that we need to see to tell us where we are stratigraphically. Okay, back to here. Now we have our little private well and then the septic system that goes with it. Let me shrink this down a little bit better. So what, with respect to aquifer protection and the mission of the Albany County Clean Water Advocates? Okay, let's go to a cartoon vision of things. Here I've identified a contaminant source. In this case, I've drawn it as it was a septic system slightly below the surface, but let's keep in mind, as I said earlier, that this can be any surface or near subsurface based contaminant source. Above the water table, there's no interference. It's just finding its way down, soaking into the ground. And that continues until it hits the water table. So in this zone, there's no opportunity for dilution particularly. Some attenuation, and this is the zone that was experimented on by the recent Lidstone report for the county using a leach field out in the Sherman Hills, and they found nitrate concentrations. Again, nitrate just as one of many potential contaminants in the 40 to 60, maybe even 75 milligram range as it made its way from the septic tank down to the water table. Now, once it hits the water table, in this case, I've just done if there was a single well out there in Sherman Hills, and then off the recharge area off to the east, we have the clean water that's moving through the aquifer, and it moves basically from east to west. The contaminants from the surface obviously are introduced into the top of the aquifer, so the contaminants are most concentrated right here, and then as they are swept into that stream, I've used the purple to indicate a certain amount of dilution. So while the nitrate concentration, for example, now we're seeing 40 to 60, 75 right here, it fairly quickly drops as it gets diluted by the clean groundwater coming in. Now, lest we think of this as a river, let me point out that these velocities across the diagram are in feet per day, sometimes inches per day. This is oozing along, it isn't flowing along, but the basic process is one of introducing a tracer, a contaminant, a tributary stream of different quality here, and it slowly diffusing itself into the aquifer. The further down here we go, the more it's going to mix, and the lower that concentration is going to be. So this is the thing that's of interest to us in terms of land use planning for what goes on up here and how it relates to what goes on down here. Now, this is the vertical view, but exactly the same thing's going on in a horizontal view. This is from one of our, the Monitor Well report. So here's East Grand, Imperial Heights, Sherman Hills here, high schools down here. This is Walmart. And so now we have in horizontal view a contaminant source of nitrates out here in Sherman Hills. And as it moves from east to west, it's slowly making its way towards discharge to the surface here at City Springs and the Turner Wells, and it becomes commingled with a whole lot of nice clean recharge coming off the hill, because there are no subdivisions above Imperial Heights. At this point, there's a new one planned right in here. So as we have this clean water groundwater stream combining with this contaminated, and I don't mean to say that it's toxic or anything, but we have measured nitrate levels that show the elevated nitrate levels here. In this particular sampling, we were at 8. That number has been as high as 9.8, I think, just less than the safe drinking water number of 10. And as we move from the contaminant source through this dilution process towards the city wells and the city springs, we have a nitrate level of 5 was measured here just outside Walmart. This little piece of ground we call the triangle, and we have a well right there. This is a monitor well at LCCC, so now we're down to 3, and by the time we get to the city municipal wells, we're down to 2. But same process is going on, and the solution to pollution is dilution works here, and it's why the folks that are most immediately impacted are the wells in this area, and then as we get down to the municipal wells, we have the advantage of substantial dilution. So it's really the same picture vertically as well as horizontally. Okay. So now let's talk about the well screen. So we've got a hole in the ground, and now we put some casing in it so that it won't collapse on us, but now we need a way for the water to get into our casing. And you'll see the word screen, which never looks like window screen, but serves the same purpose. The window screen filters the bugs out and the leaves and so forth, and the well screen filters the dirt and the rock out. So that screened section is where the water enters the well, and that process is very like this straw that you use to drink mate tea, where we would call this the well screen. We'd call this the casing, and as you draw water out of it, the screen keeps the tea leaves from sucking up into your mouth, and you end up with a cleaner stream of mate back to your user at the surface. The well equivalents come in quite a variety of forms. Just here's a picture of some well screen, as it's called. That's actually it's a PVC wire that's wrapped around and around and around in a spiral with just the right spacing in between to hold the sand back and let the water through. And anybody wants to holler in the middle of this, go right ahead. I'll just roll along. Here's the most common well screen used in the domestic wells in our area. It's slotted casing, and these slots are carefully controlled for their width. And when one finds a slot that keeps the dirt out and lets the water in, that's a balance that you have to find. Here would be some steel well screen. It doesn't look like screen. What you're looking at here is a piece of steel that was slotted with a cutting torch. And we can build these out of any material. In the big wells, you'll typically see a screen like this, but all made out of stainless steel, and in sizes anywhere from 4 inches in diameter to 24 inches in diameter. Okay, so let's think about how contamination might get into our well now that we've put our well screen into it. Requirements from time immemorial is that you have 100-foot spacing between your well and your leach field for a typical domestic system, and that continues to be required. And I say that's just standard practice. And good practice would be actually to reverse this and put the well on the up gradient side, so that when you did hit the groundwater, it was all swept away from your well. So there's that basic 100-foot minimum. But as we can see in our diagram, that's of limited usefulness as you begin to look into the subsurface. So in this particular configuration, the contamination has descended from the septic tank. It's now hitting the groundwater table. The groundwater is moving from this side to this side. west to east and sweeps it down gradient, where in this case it probably is picked up by the well. DEQ requirements, when one does an analysis of the impact on aquifers, suggest that this first 30 feet is the critical zone in which one is most likely to see the contamination from any surface source. Now, okay, so here's a shallow domestic well. Okay, let's continue our story. What this person has done, and this is the cheapest. So we've drilled the well and we go down, down, and down, and down. Then we hit the water table, and we don't want to just stop right there because then there's not much to work with. So we go down into the water a little bit so that we have some room to pull the water up and down. And if the water table drops slightly in a dry period, then our well doesn't go dry. But you're paying by the foot. So if you're being pretty skimpy, you're going to drill this well no further into the aquifer than you think you need. And thereby you're going to expose yourself to these shallower sources of contamination. So this is a typical shallow domestic well, and there are lots and lots of those out there. As I say, you're paying by the foot. The driller's finding water, maybe water squirting out of the well, and the owner is saying, well, why don't you stop? And the driller's saying, well, you ought to go a little bit deeper, and the meter is running, and so then there's an argument about how far to go. A better solution, if you're thinking ahead and want to invest the money, would be a deep domestic well. And you'll hear a lot of people say the solution to contaminated wells in the subdivisions east of Laramie is to just drill deeper. True fact. The deeper you go, as you can see on the diagram, the less subject you are to these surface sources of contamination. Now, there's about 500 wells out there, so it's never quite just you and you alone, but basically you would like to get as much of this clean groundwater and as little of this contaminated groundwater as you can. And one way to improve your odds is to drill your well deeper and then put your screens at the bottom so that you are sucking in the water here rather than sucking in the water here. So this would be a deep domestic well and would be a less vulnerable well to surface contamination. Here's an example of a production well from Imperial Heights North. You see that casing sitting there by that little bridge, if you guys are familiar with that Imperial Heights Park. This little triangle symbol is standard for the depth to water, which is what DTW stands for. So in this case, we drilled the well through a sandstone, or through, I guess, to start, a sandstone, a limestone, a sandstone in yellow, a limestone in blue, a sandstone in yellow, showing all these fractures in red, another limestone and another sandstone. And we chose to complete the well to draw our water from here. So what we've done is we put our casing down through this, and we've put cement behind it all the way to here. So the way the water gets into our well is just out of this deeper sandstone. That ensures, to the extent one can, its quality. A monitor well, and you've probably all heard me talk about how domestic wells aren't monitor wells. If you're looking for whether your crankcase is leaking or not, you look for the oil spots on the driveway, not over in the rose bed. And so there's a lot of confusion out there where somebody will say, well, I have monitored the water quality in my well and it was just fine. That isn't a monitor well in the sense of a well that was deliberately built and located and completed to monitor what the impact on groundwater is. So when we build a monitor well, dedicated monitor well, what we do is screen them right here where we're most likely to see this impact. And a shallow domestic well, wherever my shallow domestic well went, yeah, I mean that's close, but even so, any supply well is going to have been deliberately completed somewhat deeper in the aquifer than right here at the water table. So when we see data coming back from domestic wells, it is inevitably skewed away from the worst of the contamination for obvious reasons. But it's different than a monitor well for that reason.
I have a question.
Sure.
Are all contaminants basically near the surface, or don't some sink?
Yeah, good point. They're called DNAPLs, dense non-aqueous phase liquids, and they are the bane of water contaminants. There are certain industrial solvents that do that. they're called sinkers, and they're hugely problematic. Most of the things we're thinking about in terms of conventional land use would be septic effluent, which is just going to be dissolved in the water and has the same density as water, or petroleum products, which typically float. There are some hydrocarbons that sink, but gasoline, diesel, antifreeze, most of those kinds of things are less dense than water, so will tend to float. But yes, there are organic materials, liquids, industrial solvents that sink. Those missile silos over at Cheyenne, you may have heard the stories. They used these solvents to clean those back in the 60s, TCE, trichloroethylene, which is a sinker. And that's why they have air strippers on the Cheyenne municipal water supply to try to get rid of that, because to get it out of the aquifer is really hard. And then, of course, our ability we control the surface through our land use regulations, and so it's surface-based contaminants that we're most concerned about. And those are going to show up first here, even if they are headed on down to deeper zones.
So Marion's point is relevant for the I-80 corridor. If we had an industrial solvent spill there, that could go deep into the aquifer.
Yes, yes. Now, again, even I-80, the great majority of the materials of concern that run down I-80 are fuel. But yeah, occasionally a tanker goes by that's full of an industrial solvent, and the really nasty ones that just have these horrendous toxicities are being phased out. So yes, it's a concern.
I have a thing. When you say organic compounds, you're talking about compounds with carbon in them, right?
Yeah.
Not organic like organic groceries.
Right. I mean, yeah, organic compounds. Right. Yeah. Those carbon rings and alkanes and alkenes and ethylenes and 2,4,5-cis dipropylbutanes and things that people may remember from chemistry courses. And those tend to be toxic in various ways. So there's my pitch on why monitor wells are different. And we have very few of these monitor wells in the Casper Aquifer that are actually built, dedicated, located, completed as groundwater contamination monitor wells. There are like maybe 3. And here's a monitor well. This is the well that's in that little triangle piece. No, this is on the south side of Imperial Heights Park, just short of Sherman Hills. So in this case, we drilled it down through the several layers of the Casper, a sand, a lime, another sand, a lime, another sand, another lime, and then we filled it all back in because we did not want to take water from down further in the aquifer. We wanted to take water out of this sandstone. Here's our water table right here. So we've left the well open from here to here. Here's our little pump. And so this is what a monitor well properly completed and located looks like. And that well serves no other purpose than to periodically monitor the water quality at that point. So now let's talk about the well seal. So we've talked about how deep the well is in the screen, but now we have to talk about what's around my casing. In my little garden example, I was just packing this full of dirt, which would keep, mice from crawling down. But many of the older wells, particularly, the idea of the casing was just to keep the dirt from collapsing again into the well, and then when we didn't care if it collapsed or not. So there are wells out there that have nothing behind the casing, behind meaning between the casing and the borehole. And so they're susceptible to water just from the surface running off the pavement, or somebody dumps their oil out there, any darn thing, running just down along the casing. And even though the well is deep and is screened fairly deep in a clean part of the aquifer, it's going to see the contamination that's coming down alongside the casing. So you'll hear people say, oh, the aquifer isn't contaminated, it's the casings. It's kind of a bizarre thing. Well, it's a failure of the seal, and there has to be a source of contamination for there to be a problem. So you'll hear it said as though the casing itself is somehow dissolving and corrupting the water supply. Well, what that means is, yes, the way the well was completed allows easier passage of surface-based contaminants, either surface or near subsurface, to find their way either directly down the well, or in this case, even if I've just contaminated the top of the aquifer, remember I'm sucking water out here, so it's going to want to come into the well and go down and come back out my well. So this is the poorest well completion, and there are plenty of those out there. The next, and still quite common, is where you filled that annular space, the space between the casing and the borehole, with gravel. Get thrown in to help keep the dirt out of your screen is the main purpose for it, and to hold the sides of the well out. But once you're throwing gravel into that cavity, it's quite common in the older days to have filled it clear to the surface. So yes, it inhibits the flow of water off the surface and down the sides, or even through the aquifer and down the sides, but it certainly does not preclude it. It's harder to run through a donut of gravel than it is through just open air, but still, this is certainly less than a desirable way to finish up a well. And there are lots of those out there. Better is something that has a surface seal, at least, where for the first 10, 20 feet, we've surrounded the casing with cement. So now I've precluded material running across the surface and down the well. And that's good. And this is required now of any well that is drilled in the state of Wyoming, if it complies with the minimum well construction standards. And all the drillers in Wyoming these days, as of the last 8 years, 10 years, are required to be licensed and to conform with these kind of most basic construction standards. It does not, however, protect my well screen from contaminants that soak down, not going down the well casing, but just in the ground in the dirt, like my septic system here, from getting into the top of the aquifer and again running down through the gravel pack, getting in the screen. So better, but you're still not quite there. Best and most expensive, and therefore less common, is to surround that casing with cement all the way through the aquifer to the place where you want to get the water. So this construction makes sure that the only way water can get into this well is from these zones rather than from these zones. So this is the way you would properly complete a well. And if you do so, your chances of contamination are less. Now, what happens up here in terms of contamination that's going to find its way to here is a different story. But this is the best you can do for yourself. And so here's a slide I put together 10 years ago for the little science panel that we presented, showing when you put all those things I just talked about together, why you get quite a complicated picture when you start trying to trace aquifer contamination by sampling domestic wells. So just to walk you quickly through the diagram, here's a contaminant source. Here's a guy with a good seal on his well, his or her, and so the contamination in this case is going to go down. It maybe is going to hit this limestone layer and have a little harder time getting through it, so it runs along on top of it. You got a nice seal, and you got a pretty good well. Next well is the well itself produces pretty good quality water, but there's no seal. So in this case, this contamination now has run down the poor seal around that well and found its way into the aquifer. That means the next guy, even though he has a well-sealed well, and he's tried to get down into the aquifer a little ways, he's going to see by this path the results of a contaminant source up here. In this case, a contaminant source finds its way down into the aquifer through a fracture zone, and there are lots and lots of those in the Casper. And by that method, finds its way into this well. So here's a well that I've colored red as an impacted well, even though it might be properly constructed and tightly sealed through this layer. Another source of contamination is moving downward, finding its way into the water table. This well is unimpacted because it's well sealed and it's deeper, but this guy down here is going to see that contamination coming into the well. So when one says, oh, well, if all of this septic stuff and residential contaminant were true, we would see in Sherman Hills, for example, good wells here, middle-ish wells here, poor wells down here. It's because of these relationships that's very confusing. And when you're dependent on sampling of domestic wells, you have to try to tease out a much more complicated picture. And it's why I can get a 2 nitrate there and a 6 here and a 12 there and a 1 there and a 7 there. And that's what you actually see. So again, we shouldn't be distracted by the noise in the data. It's a function of a whole lot of individual decisions as individual wells were drilled. What does a well look like? What does groundwater look like? This is always a frustration because we hydrogeologists don't have much to show, like a big bridge or a new school building. This, for example, is the Imperial Heights South Monitor well. Nothing very exciting there. Poured a little cement around it to keep your feet from getting muddy as you're sampling it, and to keep surface material away from the wellbore itself. Typically, what you'll see in a PVC well, here's that PVC casing, and the steel is just a guard casing. So the steel is planted in the ground 4 or 5 feet. It's just to keep people from running into it and breaking it off. But this is what you see inside a typical monitor well. Big municipal wells. This is Turner number 1, one of the big wells for the city. What's to see? Well, you see a little shed like that one out below City Spring. Here's a picture of what one might see inside of it. This is actually a well up at Newcastle that's a flowing well and is leaking. That's where this picture was taken. So inside those little brown buildings, you see a hole. Whoop, it isn't. You're not seeing what I'm seeing? Oh, well, when did I lose you?
Back at the monitor. Stuck on the monitor one.
Oh. Oh, well, you didn't see this one with all the red dots and blue dots? Okay. On that one? Okay, now I'm looking at a shed, Sarah? Huh. Well, I don't know how to just change that. Should I stop sharing? And then try sharing again? Okay, now do you see a building? Okay, and then this is where I was saying, now you should be seeing inside the building. Okay, and we're just about to the end here, but I'm just saying that if you look in those doors, you see valves and pipes and meters and backflow preventers and one thing and another. The rare opportunities we have to actually see what a well looks like are this one, which you should be seeing 3 downhole pictures. Is that right? Are you seeing 3 little pictures? Anybody?
Yes, we're seeing 3 little.
Okay, these are pictures from down inside that triangle well, the one out there by Walmart, and what was fun about this is we're actually seeing now these cracks in the rock down below. So here we are. Oh, I guess these are in feet now. So here we are 125 feet deep. We see this big crack that the water's running through. And the picture here is we've just taken a picture all the way around the well bore and then slid it down one side and opened it up. So what you're seeing is a 360-degree view of what the well bore looks like. And back to our